This physics question is about torque and involves a 60 centimeter long ruler and with a fulcrum that is placed at the 40 centimeter mark. And we want to know where we can place a 0.2 kilogram mass in order to balance this left side of the fulcrum. So we first have to find the halfway point of the rod. Well, the rod's 60 centimeters, not very difficult to divide that by 2 and find 30 centimeters as the halfway point. From there, we then want to subtract the amount from the left of the pivot point, or where the pivot point is placed. We want to subtract the center from that, and we get a value of 10 centimeters, and that's this value. That's the radius in between the fulcrum and the center of the ruler. So we found that gives that the center of rod is 10 centimeters from the reference point, and the reference point being 40 centimeters where the pivot point is placed. So then we can then take the fulcrum as the pivot point, and the counterclockwise torque is due to the rod's weight. So what we next want to find is the torque in the counterclockwise direction, which is without the mass. So if we pretend this isn't here yet, we know if we place a fulcrum not in the center of mass or in the center of the ruler, that this side is going to lean down and it's going to fall. And so we want to know where to place. Well, we want to calculate this counterclockwise torque first. So we know that if this side falls, we start with this side. Since this side's going to go up, we know that this is positive torque, so it's going to move in this direction. And so to calculate torque, we use the force times the radius times sine of theta. Well, in this situation, there is no angle, so theta is just 90 degrees, and sine of 90 degrees is 1. So really, in this type of situation, we can just sort of disregard that. So we have the total force times the radius. Well, the total force in this situation is the mass of the ruler times the gravity times the radius. And the radius being this 10 centimeters between the center of the ruler to the fulcrum point. And so we get we plug those values in. Kilograms cancels out. We're left with newtons times newtons times meters, and we get this value in our units of newton meters. Then we want to calculate the clockwise torque, because if we put Sorry about that. So if we want to then calculate the clockwise torque is going to be once we put this hanging mass here. So once this hanging mass is here, the motion of the ruler is going to go down, or clockwise. And so this is going to go up, this is going to go down. Well, we still know that the total force is the mass times the gravity. But in this case, we don't know the radius. That's what we're looking for. We're looking for this value between the fulcrum and the hanging mass, where we need to place it in order to balance this extra weight on this left side of the ruler. So we're looking for our variable r, or the radius. So we plug these values in, the mass times the gravity of the hanging mass times the gravity, and we set that equal to this counterclockwise force. And that way, we want to set this equal to the clockwise force due to the additional mass to find the distance, or the radius, from the fulcrum, or the pivot point. So we divide by this value, which turns out to be 5.886 newtons. Divide that on both sides to cancel it out and get our variable r by itself. We're left with just meters because newtons cancels out. So we get that our radius is 0.033 meters to the right of the pivot point. So, or what that means is that we want our hanging mass 3.33 centimeters from the fulcrum, or our fulcrum being placed at 40 centimeters plus 3.33 centimeters, we want it 43.33 centimeters from the left side of this ruler in order to balance this weight.